This problem asks us to calculate the transverse shear stress at the neutral axis along a beam where we have some internal shear force V. So what you see here are the kind of general representations for what we use to calculate the transverse shear stress, including the shear formula, which is that the internal shear force times the first moment of area divided by the second moment of area times the width or the thickness of the beam will give us the transverse shear stress. Now, we're looking at the shear stress, the transverse shear stress at the neutral axis. So let's go ahead and redraw the cross section such that we have the neutral axis more or less going through the middle, and the area that's going to be of concern for us, the A prime, is going to be starting from the neutral axis where y prime is equal to 0 and going to the top surface. We will say that the centroid of this A prime is going to be given by a y bar prime. Now, to calculate the first moment of area, Q, we have this integral equation, or integral-based equation, that the integral of y prime dA prime is equal to the first moment of area. And as you saw in the notes in our previous discussion, we can also say that the distance to the centroid given by this y bar prime is going to be times A prime is going to be the first moment of area Q. So instead of having to solve this integral, we can use some geometry to be able to calculate Q, which is typically the hardest portion of these types of problems, and then be able to calculate the transverse shear stress. The height is given by h for this section, and the y bar prime will therefore be equal to half the h over 2. So you see h over 2 would just be this top portion, and then we're going halfway up of that, so we can take half of that. And so that would give us h over 4 for y bar prime. For the width, we have b, okay? And I often say width. Hibbler's book will call this a t, thickness. All right, but b is equal to t, and a prime is equal to this h over 2 height times b. Okay? And as I just said, b is equal to t. So when it comes to this portion of the equation, the t, we have a substitution of b. The second moment of area is taken over the entire cross section, regardless of where we might be asked to calculate the transverse shear stress. So if we're calculating it up here, or like at this location or this location, wherever it might be, we were going to say that the second moment of area is not changing, but is dictated completely by the overall thickness, the overall width, and we have previously described this equation when we were doing beam bending. So bh cubed over 12. We can rewrite that tau is equal to VQ over IT, like we have here, and we can substitute the parameters that we have been solving. So we have an I, that's the BH cubed over 12. We have a B, which is the width here. The V is given in the problem, so we just have V there. And then the Q is equal to this Y bar prime times the A prime. So that's going to be this h over 4 down here, and we're going to have our h over 2 times b that we put over here. So when we solve this problem out in its entirety, what we get is that the transverse shear stress at the neutral axis is going to be equal to 3 times v over 2bh. And this representation, or this formula, has another way of being written that is often useful for calculating out the maximum shear stress in a rectangular cross section, maximum transverse shear stress, better said. If we know the average shear stress, which in this case would just be the V, the shear force, divided by BH, we can multiply simply by 3/2 to get the maximum shear transverse shear stress. So we maybe are adding a couple more details. One, that the maximum transverse shear stress does in fact happen at the neutral axis, as we discussed in class. And two, we can figure out what the average shear stress is, which is usually quite simple, and just multiply by 3/2. Okay, thank you. I hope you find this video helpful.